All right, students, welcome to week 5. So this is our lecture portion for the night. A couple things to go over since I know not everybody will be able to make the Zoom. Let me start with a few things. So if you go into our course from the dashboard, if you go under modules, right down here, you will see our week 5 modules. So here's a link to the discussion board. And so once again, I just give you a brief little overview. This is a short video. And then you just have to answer this question. How was Mendeleev able to predict the properties of undiscovered elements? So let me talk about the discussions real quick because I had mentioned in my email earlier, it's a little disheartening to see such little participation, especially in these discussion boards. These are the replies, and so out of 22 people in the class, I mean, I'm averaging like around 7 replies here. And that's one because this one was 13. This is part of your required grade or the requirements for your grade. So don't neglect that. Otherwise, it will be reflected on your grade at the end. So all you got to do is come over, hit week 5 discussion board, or go to it from the modules, and it'll be right there waiting for you. Secondly, is the periodic table Prezi link. So tonight I did not do a PowerPoint. Instead, I'm opting to use this presentation on Prezi from a person I know who did a great job on it. And so it just makes it easier. And this is the link to that. Once I'm done recording, there will be another page here with the link to YouTube for this lecture. So just a couple unfun things that we got to go over. So ck12.org. So your new unit is up, your new assignments is up. When I'm looking here, so if I look at week 3 work, only 4 people have it done. And then when I look at week 4 work, even less, only 1. So we got to get on that. Let me show you. So this is a screen grab from the gradebook. And so you can see a lot of blanks here. Each one of these lines here or these rows is a student in the class. And so lots of blanks. And so a couple words of warning. A lot of people save this, or I shouldn't say save this. A lot of people wait to do these assignments till the very end. Not good, and it's not going to work. Because if there's 5 weeks of inactivity, I have to drop you from the course. I told you nobody fails my class, but at the same time, if you're not doing the work, you're not going to remain in the class. So my biggest piece of advice to you would be to start cranking through some of this work, because this is week 5. So if I don't start to see some participation from some of these blanks here, then I got to start dropping. Because if you're not communicating with me and also not doing the work, there's really nothing more I can do. Okay, so that's all the unfun stuff. And so if you go into your assignments for CK12, you will see this one that says no due date. But if you click on it, it says week 5 periodic table. So once again, you just click on that and you start to go through each of the sections. And I'll show you on here, just like I'll show you during the Zoom. But you click on one of them, and when it comes up, you're going to have a few things here. Now, the adaptive practice is the practice portion of this section of the unit, meaning that it's going to ask you a series of questions and want you to get 10 of them right. And now you'll have tonight's presentation that you can always go back and watch. And then you also have articles you can read, videos you can watch, and real-world applications you could use to help you answer some of those questions. And so once you're done with those and you feel comfortable, you go into the adaptive practice, you answer those questions, you move on to the next section. And you can see these are the sections here. So there's a decent amount. So this is why you don't want to wait on this type of thing. It'll become insurmountable. And then also, if you're not doing it, I have to assume that you're just not going to participate in the class, which I don't want to do. But so anyway, last of the unfun stuff. So now it's done. So back to what we're going to do tonight. We're going to talk about the periodic table. So let me expand this. And so we have seen this in any science classroom you've been in, any chemistry classroom you've been in. It's very popular to put on T-shirts. I've even seen people with tattoos of this. Now, disregard this page 13 or 130 through 160 in the textbook. It was done by this gentleman right here for his in-class class. So we want to talk about this periodic table because it is not just a haphazard arrangement. You can clearly tell it doesn't go by alphabetical order, and it's not arranged in the sequence in which they were discovered. It's a very complicated and very impressive piece of scientific achievement, and we're going to go through sort of how to read it because it's very, very important for all the sciences. And we're used to seeing this one because this is the most sensical one to start with. But there are periodic tables that look very different, and we'll see some of those at the end. Okay, so a question we want to ask ourselves as we're going through, is there a reason why the elements are arranged the way they are in the periodic table? And the answer is absolutely yes. And we're going to see why they are arranged the way that they are. And hopefully you've watched the video or will watch the video on Dmitry Mendeleev and understand just how powerful of a scientific mind he had, to where he was able to create a table that had missing pieces, but he was able to predict what was going to go in there based off of the properties of similar elements around it. So if you recall from last week, some of you, or even the week before, some of you may not because you haven't done the work, which you should be doing. But an element is a pure substance consisting of a single atom. And then in 1869, there was less than 70 known elements. And if we hop back, I don't know if it'll let me do it. Yeah, well, if we look at it now, I mean, we're going all the way up through 118. That's pretty impressive. So we've come a long, long way in just a short amount of time. And so Russian scientist Dmitry Mendeleev discovered a set of patterns that he applied to all elements. And that's one of the best scientific steps you can take, is to recognize patterns. Because once you can do that, you can start to understand what's going on. And so because he was able to see these patterns, it's almost like a numbers game. He was able to see patterns and then predict empty spots on the periodic table and what should go there. He would be able to predict, like you'll see in the discussion board video, how much it would weigh, what its melting point would be, what its energy level is. He was able to predict all those things without even having it been discovered. We still discover elements today that can be predicted from Mendeleev's work. It's pretty amazing. And so these are some of our first modern periodic tables. So if we look at this one here, what I love about it is we recognize some of the ones on there, like hydrogen, beryllium, boron, carbon. But then as we go through, you can start to see, like, especially after calcium, like right in here, question mark, didn't know. But he knew, and we'll get to this, what this would be. He knew what the atomic number would be. And so he was able to, based off of elements that were known and discovered, make predictions that were incredibly accurate about unknown ones based off of that atomic number. All right, and so this is some of like the beginning ones and how it was sort of started. And we can see it has familiar symptoms of our current periodic table, but it has changed vastly over time, which is really neat. So the basic breakdown of our periodic table. So now this is just I'll say the tile you would see on the periodic table for carbon. And so hopefully if you've done the work or watched the lectures from the previous weeks, and I know a lot of people haven't been watching the videos or the lectures, and to that I say, best of luck. Hope you don't get dropped. But so the atomic number is the number of protons that are in the nucleus of the atom. It defines the atom. So carbon, 6 protons in the nucleus. We can see that this tile also gives us the element name, gives us the chemical symbol. So for carbon it's just C, and then tells us our atomic mass. And so this is the average mass of all the atoms in an element. Because if you remember, we can have isotopes, which are a different number of neutrons than protons. So because of that, there can be different versions of carbon, different flavors of carbon, if you will. And this number here is just all of the masses. So if you added up, a bunch of the different isotopes and then averaged them out, you would get 12.01. And so that's what we see on the periodic table, all these symbols on these tiles that have so much information that we can read through. And so we have the element name, usually from a Greek or Latin word. One of my favorite ones is lead. So lead on the periodic table has the symbol of Pb, which sounds kind of weird. Why would lead have Pb? But it is because in old times, lead was called plumbum. And that's what the Romans used to line their pipes with to transport water. And it has applications today because it was called plumbum. And if you have problems with your pipes nowadays, you call the plumber. Kind of cool. I like how things work out like that. So the symbol is just a shorthand abbreviation, and it's usually based off of the Greek or Latin word, which is why we have some that don't seem to match up, like Hg for mercury, and like I was just saying, Pb for lead. And so it's usually based off of that Greek or Latin term. And then, so like I said, we have the atomic number, which is just the number of protons, which will always be the same. And if it's neutral, which everything is on the periodic table, it's important to note that this is the number of electrons as well. So everything on the periodic table is neutral. It has the same number of protons and electrons. Therefore, this 6, meaning 6 protons, also means 6 electrons. The atomic mass, like we said, is just the average protons and neutrons. That would be their average mass. And so that's a breakdown of each tile, if you will. So we just talked about isotopes, different number of neutrons. Some of them are very rare, some of them are very common, but they do exist, and that's what we call an isotope. So carbon could have 6 protons in the nucleus, and it could have 6 neutrons in the nucleus too. But it can have 6 protons in the nucleus and 8 protons in the nucleus. Let me back that up. So it can have 6 protons in the nucleus if it's carbon. It can have 6 neutrons, or it can have 8 neutrons, or some have 12 neutrons, some have 14 neutrons. It's just a different number, but all of them are carbon because there's 6 protons. And then the isotope is just when those protons and neutrons don't balance out. Okay, and there's our atomic number, symbol, name, and atomic mass for zirconium. Number 40 on the periodic table, meaning that there are 40 protons and 40 electrons in its ground state and its neutral state, meaning that the protons and electrons balance out. The symbol for zirconium, Zr, this one's pretty straightforward. And there's your atomic mass, meaning if you added up the protons and neutrons of all the isotopes, there's your average. Okay, so now we're going to talk about each of these as we go through, because there's periods and there's groups and there's families, and they're all very, very important. So the periods and groups. So the periodic table is organized into periods and groups, and the periods, the atomic number and the mass increase as you go from left to right. So you'll notice like hydrogen is number 1, helium is number 2. So it's almost like reading a book. As you go from left to right, that atomic number and mass will increase. And then as you go from left to right, the properties of the elements change as well. Now they could be similar, but they will start to change as you go across those properties. As you go across those periods. So, went too far. So right here we have period 1, which includes hydrogen, and way over here helium. We have period 2, lithium and beryllium. So you can just see, you just start at the top and you go down numerically and sequentially naming the periods. So period 1, period 2, period 3, and so forth. And then we can see over here, once again, this still matches up with period 1, this still matches up with period 2. So it goes across the whole thing, left to right, just like reading a book. And once again, here's a shout out to my man who made this. Great teacher, great friend. Alrighty, so then we see more down here. Here's periods 4, 5, 6. And then we get to these cool little areas in here, which we'll talk about in just a second. And you can see, so it goes from 56, and then over here it jumps to 72. But all those elements from 57 to 71, we're going to see that they sort of get pulled out. Same with elements 89 to 103. So groups or families, which they can also be called, designate elements with similar reactive characteristics. So we're going to see a video once this is all done about reactivity with certain metals in the alkali group, which we're going to get to. So if we're talking about groups, groups are these columns as we go through. So you have here 1, or they'll call 1A, 2, 2A, and then it goes all the way across over here to row 18. This area in the middle here, we'll get to them in a little bit. They're called transition metals. And then on the left and right side are what we call the representative elements, meaning that these are very, very common in nature. We see them all the time. These ones here, they are common, but sometimes they get a little messy and muddy in their properties, and they're not as reliable as these ones on the left and right sides. But so we have our groups and our families in these columns. Some of them have special names, which we will get to. But so you would say like period 1 is everything up in here. Period 4 is everything through here. Then if you want to say group 1, well, group 1 would be everything top and bottom. And you could say group 8 or group 18 if you wanted to. And that would be everything top to bottom over here. So let's talk about the metals. We want to hop back. My apologies. So the metals, pretty much if you follow, let's see if I want to use the drawing tool again. I don't know if I do. I'm going to give it a whirl. So everything going through this way and then back. Man, I am a terrible tracer. These are metals. Now, what we're going to talk about first are the ones in here. But yeah, so everything that I sort of encompass, so everything pretty much on the left side and in the middle, it is a metal. So let's progress from there. Oh no, let's see if I can get rid of that thing. Nope, don't want to hide the tools, want to get rid of it. So let's see how I get rid of this. All right, there we go. I just had to escape. Oh, please don't tell me I have to deal with this anymore. Forgive me for this. I'll try to erase these markings. Oh boy. This is not going to be fun. All right. We already talked about all these. All right, so let me hop out of this and let me get rid of this marking. Just give me 1 second. I'll tell you what I'll do. I'm just going to copy and paste because I don't want to start this whole thing over. And that's my way around that. Okay. Sorry if you hear sirens outside my apartment here. We'll wait till they pass through. So let's get back to where we were, and I promise I will never use the marking tool again, at least not until next week. So we talked about periods and groups. And now we talked about where the metals were, and now we're going to get into the metals. All right. So here we go. So the metals, they dominate the periodic table. They make up 91 out of the 118 known elements. I like that, known elements. There might be more that we don't know. If you ever want some fun little mental stuff to chew on, look up element 115 and its history. It is pretty interesting. So all metals share the following characteristics to a certain degree, meaning that it may not be identical, but they share these characteristics. That they all have a luster, which means that they're shiny. They are ductile, which means you can hammer them out into a flat sheet. You can twist them into wire. And you can think of some of your common metals like copper, silver, gold. These are things you can do, with metals. They're very malleable and ductile. So top right here, they're malleable. They can be hammered. They can be stretched. And they're all great conductors of heat and electricity, meaning that if you go and stick a fork in a light socket, which you should not do, it is going to conduct that electricity so well into your body that you will do serious damage to yourself. So don't do that. Conversely, if you went and you stuck a wooden fork, if you had a wooden fork for some reason, into a light socket, you'd be good. It's not a metal. It's not going to conduct it. Once again, though, don't do it. You're probably going to do some serious damage to the wiring there. So, and there's some of our shininess as we browse through these. We can see, so we got like a graphite in there. We have some like molybdenum. We have these different elements here. So there's like a good, without physically handling this, I would say that's a copper piece or a gold piece. You have some what's called chalcopyrite, and you have bismuth. And these are all made up of various elements. And so they said they're all malleable. They can be hammered out flat. So there you go. You got a kilogram of fine gold right there that can be flattened out into those discs. That's pretty neat. We can have sort of sheet metal, like some of us are very familiar with, tubing, pipes, wrought iron, whatever that thing is. I don't know. But once again, maybe it's like a silver alloy, or here we go, nice little candle holders, which is probably sterling silver. And silver being one of our elements, it is a very bendable and malleable element there. Ductile, meaning they could be put into solenoids, if you're familiar with those. They can be sort of stretched out in a string, so you could have steel string, which was just an alloy of a couple different metals, and they can be used for conducting heat and electricity. If you like to play video games, all like the best HDMI cables have like gold plating, because gold is a great conductor of heat and electricity. And so the electricity that it can conduct can get those signals to and from your TV to your gaming system and back in no time. All right, so yeah, that looks hot. So you can see it conducts heat and electricity. So the heat you're seeing conducted means like it'll hold it and it'll transfer it about. It's just like your pots and pans on the stove. Even though the flame's concentrated, in that one area, it'll conduct the heat all around the pan to where the whole thing is hot. So spark plugs are part of it. And then, electrical wiring absolutely is a characteristic of a metal. And so all metals will undergo what's called corrosion when they react with oxygen. It could be iron oxide, like iron will corrode into iron oxide, which is just rust. And there are a lot of different oxides that metals will turn into. There you go. All right. So a couple questions for us to keep in mind. Who was Dmitry Mendeleev? Hopefully you can answer that now. You will have questions on that on your CK12. Another thing to consider. What is the difference between the atomic number and the atomic mass? Bare bones. Basic answer would be atomic number is the number of protons in the nucleus. Atomic mass, protons and neutrons in the nucleus. Boom, done. So these are things to keep in mind, especially as you're going to be going through your CK12 work. And then, so what are the characteristics of all metals? Well, that's what we just saw. They're ductile, they're malleable, they're shiny, they have a luster, and they conduct heat and electricity very, very well. And then what is the purpose of the periods and the groups in the periodic table? It is to gather elements that have or that share similar properties, to get them around each other. So that is the main thing, to group them by their chemical characteristics, their reactivity, and other traits that they share in common. So moving on, like I said, some of the groups, which are those vertical columns, have special names, and these ones are really important. So group 1 is the alkali metals. They're the most reactive. We're going to watch a video based off of these metals, and you're going to see just how much they react with water. And they also will react with just air. If you had pure sodium or lithium or potassium and you were able to cut it, and you can cut it easily because these metals are super soft, they react with air so quickly that they corrode super fast. Most metals are soft. I know that sounds weird, but they're hardened through different processes. And these metals, I'm sorry this is cut off, but it says they are never found in their pure form in nature, meaning that they have chemically combined with other elements to make up, whether it be like minerals or anything of that sense. So you wouldn't be walking like out on a hike and be like, oh, look, there's a chunk of lithium. Wouldn't happen. It'd be tied up with something else. You could say, oh, look, there's lithium oxide tied up in that rock, which I doubt you'd say, but you could. So we can see there, they're usually kept in oil to keep them from reacting with air. Some of them, like potassium, is so reactive with air that it is a contact explosive. So if you had like a chunk of potassium sitting around for a long time, you would actually need the bomb squad to come and take it out. All right. So that was supposed to be a little thing on corrosion, but we're not going to worry about it. And so the only exception on those alkali earth metals is the very first element that we have, which is hydrogen. Now it fits in with a lot of the same chemical characteristics as the alkali earth metals, but hydrogen is a gas. So it is not a metal. It just shares some of those properties. It's kind of one of those weird ones, but it is the most abundant element in the universe. So it gets number one. Alrighty, so there we go. There's all of our alkali earth metals: hydrogen, lithium, sodium, potassium, rubidium, cesium, and francium. Now, it might strike you as weird. You might think sodium, isn't that salt? Well, it is when it's combined with chlorine, which we're going to see a little bit later on. So chlorine is a poisonous gas. Sodium is an explosive metal. But when those two chemically combine, they make table salt. That's so NaCl, if you've ever heard that chemical formula, that is just salt. And it's just a chemical combination of sodium and chlorine. So we had talked about scientific literacy when people say like, oh, I don't want any chemicals in my food. Everything is a chemical. Everything is. It's just a matter of how it's combined. If you went to go try to eat sodium, you're going to have a bad time because it's it's an explosive metal. If you went to go get some chlorine gas, you will not survive. But if you combine those two, they combine in a way that they are very stable and it creates something delicious. It's the miracle of chemistry, the magic of chemistry, if you will. All right. So group 2, that second column, is the alkali earth metals. So they are not as reactive as group 1, but they are still very reactive. And most are hard and gray and white in color. And also, once again, they're never found in their pure form in nature. These are another group that sort of chemically combine a lot of times with oxygen to create different oxides. And so you'll have magnesium strips. You'll have, and we'll hop out and look at, let me hop back real quick to where it shows our whole periodic table. So you can have the magnesium strips and you can have calcium and strontium. And these are some of the brightest burning elements. So these are really, really important when it comes to like fireworks and stuff, which is pretty cool. So as we went through those, so we'd have, magnesium chips and we'd have calcium on its own, which once again, when it's chemically combined with other things, is very healthy for you, but you wouldn't want to eat it just as it is in its native form. Look at this group in here. So let me hop back. So this muddy middle group here, so these are called the transition metals. Now, the reason they're called transition is they have what are called different valence charges. We're not going to get into it. But the other elements that we look at, their charges are always set. They don't change, but these ones do. Not something that we need to know. That's what we're calling them, the transition metals. So most of the metals on the periodic table fall in there into that middle group. So they're not very reactive like the ones in groups 1 and 2. Some are, some aren't. Most are hard and shiny and excellent conductors. This is where we find silver. This is where we find chromium. This is where we find copper. And this is where we find gold. So we look through some of them there. And you could have different things like hematite found in there. You can have molybdenum found in there. You can have like pretty, silver bars, just like there are gold bars. And so those are transition metals. And you can see some of them right here. I mean, in some of them you'll know: palladium, silver, cadmium, mercury, gold. These are all of our transition metals. They have that shininess to them. Now, mercury at room temperature is a liquid, so it doesn't fit into that category of it's a hard substance, but it does share similar chemical characteristics of those around it. So groups 13 through 15 are mixed. These are what we call metalloids, or the semi-metals. They're similar to the transition metals for the most part, but some of them have very different properties than metals. And so we're not going to worry about going through each one because we have like arsenic. Some of those were boron. The first one with little pellets was silicon. But we can see them, they start to go through this area here. This is what we call the little like zigzag of the periodic table, how it sort of stair steps all the way down. And so anything kind of touching this little zigzag is a metalloid or a semi-metal. And it is just one of those sort of weird nebulous groups of the periodic table. Whoa, we turn there. So groups 13 through 16, those are the mixed metalloids. So they're a cross between a metal and a non-metal. Some of them have a metallic luster, some don't. Some are brittle, some are really good conductors. Some are just semiconductors and they don't conduct heat and electricity very well. So these ones are very different. And we're going to see some of those in there. And as we move out, so the ones that we just went through in there, so we went through selenium and we went through bromine. No, not sorry, phosphorus. I was looking ahead there. So we went through those two elements. You can see how weird they look when they're on their own, but when they combine, they give us some pretty cool looking structures there. And then groups 14 through 16. So these are our non-metals. So they are not shiny and pretty. They are very dull. They are brittle, which means you can break them apart really easily. And they are poor conductors, meaning that they do not conduct electricity. They are what is called insulators. So we can have conductors or insulators, and most of these elements are insulators. I don't even know what that one is right there. Hold on, let me back up. We are talking about... Okay, there we go. So our non-metals. And so we can have stuff in there. So I know the next one I'm going to hop to real quick is sulfur. So that is native sulfur on its own. This element in here, if I had to guess, just looking at what I have to work on, that's going to be selenium. It's going to have that property of being dull and gray. You can break it apart, similar to the sulfur example here that you can break apart, scratch it, and it'll smell like rotten eggs. It's pretty cool. Then we can have like, let me hop out of there. So that last one there, polonium, that is one that is can be radioactive, which is pretty cool. Then we have some gases, some native gases in there too, like oxygen, nitrogen. Those are typically a gaseous form, as opposed to being like hard and brittle. So group 17, so this is the second to the last group. So this is once again a non-metal group. And they have a special name called the halogens. So the halogens are all toxic. And so we're going to look at that group in a minute. So they are the most reactive non-metals. So we had the alkali metals that were the most reactive metals. And then we have the halogens, which are the most reactive non-metals. And so let me hop back really quick so we can look at it. And so that's this whole group right here. So fluorine, chlorine, bromine, iodine, astatine, and then, that's a heck of a name. Unseptium. How much fun is that? But anyway, so chlorine, very poisonous gas. Bromine gas, deadly. Fluorine gas, deadly. And so these are very, very reactive. And so that's what makes them so dangerous on their own. But like I said, if you chemically combine them, they can be totally safe. And so there we have some of our gases. We have like chlorine gas. That's chlorine gas because it has like that brown. Then you have like neon gas in there. Let's see if we have another one in there. So that's when we're getting towards the bottom. So they can be chemically combined with other things to put them in a solid form, which if we're looking at that there, that's iodine. So then lastly, let's look at group 18. So these ones are called the noble gases. Now, everything aside from this group on the periodic table is what we'll call not stable, meaning that it is looking to chemically combine with something else. It is looking to trade electrons with other elements, or steal an electron, or share an electron, or give one away, but not group 18, not the noble gases. They are not very chemically reactive. And the reason is because their outer electron shell is filled. We don't need to get into all that, but that's why. But so they are used in lighting and photography. So they are, very, very useful. And so you have these gases, and if you pass electric current through them, the electrons in it get excited and they jump to a higher energy state and then fall down. And as they fall down, they give off light. It's kind of a cool thing. But so the noble gases, neon absolutely being one of them. That is, very popular for line sighting or sign lighting. And then we can get some of these gases when we have stars explode into nebula. It's really, really cool thing. Then you can have like halogen lights. Let me hop back. It's not going to let me hop back to it. But so you can have and this is including helium. You're looking at xenon. So xenon is putting some of those lights. And now let's transition in here because this video is running a little long to what are called the rare earth minerals. Those two areas. So we hop back. Remember there was those areas right up in here where we had like this big jump in numbers. We went from like 56, then we jumped that whole way across. Well, here they all are. So all of these ones would fit in there. It would just look really weird on the periodic table if they tried to cram those on in. And so we have two sets of the rare earths. There's the lanthanides and the actinides. They are rarely used on their own. And so on their own, they don't have much of a use. But if you combine them with other metals, then you get some really cool stuff. Like if you look up, let me hop back real quick here. Right here, neodymium. These are some of the most powerful magnets on the planet, if not the most powerful planet or magnets on the planet. So you can look up YouTube videos of those smooshing things. It's pretty fun. So they make strong magnets. And then so we see some of them in there. So you're going to have neodymium. You're going to have thorium. You're going to have these different ones that are in that series. All right. Oops. I'm sorry. Thorium's for the actinides. But so you had like lanthanum, neodymium, euporium, terbium. Those ones are all part of the lanthanides. And then you can see here the actinides. These are all in red, which include thorium, uranium, which is my favorite one, plutonium. So these are all very unique elements. And then they're unique when they are chemically combined. Like we were saying, it's all about how these are combined. And the cool thing is they're all radioactive. I shouldn't say cool, but I think it's a neat thing because radioactivity, which we'll talk about at a different point, is pretty neat. So since they're radioactive, they're all unstable, which means that they're undergoing nuclear reactions, which means that they are spontaneously changing into other elements, which is really cool. Some of them do it at a regular time interval, which is how we can do like some carbon dating, or not carbon dating, some like age dating. So like with rocks, you can use rubidium and strontium, or you can use like thorium and how it decays to determine how old the rock is. Once again, most are not naturally occurring, especially after uranium. Uranium is kind of the cutoff point for how big a nucleus can get before it becomes way too unstable and then starts to break down in these chemical reactions. But a very interesting chemical group nonetheless. So there's some of them. So there's actinium, there's uranium. This was such a key element in terms of developing the atomic bomb, which is an interesting story. But this was also like if you crush it up and you put it with some of its like other oxides, you get this really pretty orange color. And people used to use this for like to coat plates, like dinner plates. And so if you ever heard of like Fiesta ware, they used uranium. And to this day, if you were to find some Fiesta ware and get like a little Geiger counter or radioactivity detector, it would start to go off when you went around these plates, and people were just eating off of them like it was nothing. But that was before we really knew more about it. All right, so following up just with the questions. So what can we find in group one? We saw there, we had the alkali metals. All those ones that were so reactive, like the most reactive metals, that's what we found in group one. Group two, those were alkali earth metals. That was the magnesium and the calcium, and just really important elements that make up a lot of compounds that we find both on the earth and that we find out in space as well. So if you were to tell me all about the transition metals, it would take you quite a bit of time. The best thing we can say about the transition metals is that they are metals. They hold the properties of metals, And they are transitioning as we go from left to right over to the nonmetals. The properties are somewhat changing as we move from left to right. But they're that middle area where things can get kind of weird. So what about semimetals and metalloids? Where these are elements that don't necessarily have all the properties of metals, but they have some of the properties of metals. Therefore, we call them semi-metals. They're kind of metals, or metalloids. They're representative of it. So we can't qualify them as being metals because of different chemical properties, but they hold some similar ones, meaning that they may be good conductors or they may be malleable, but some of them aren't. So we can't say these groups are metals because of those reasons. And then the halogens. So we saw that those were the most reactive non-metals. That it was a lot of gases in there, but they were sort of the non-metal equivalent of the alkali metals, meaning that they were super reactive, and that whole group going top to bottom is very chemically active and will combine with other elements. And then lastly, what can we find in group 18? Well, that was just our noble gases, those non-reactive gases that are very stable. Their outer shell is full of electrons. They're not looking to chemically combine with anything. So they're sort of happy on their own. And so the lanthanides, those were just part of the rare earth minerals. There's nothing more we need to say about those. I don't ask you too much about those on the CK12 stuff, if at all. And the same thing about the actinides. So these ones were all radioactive. Once again, part of that series that sort of gets pulled out of the periodic table and still part of the rare earth elements. So I was telling you, our periodic table is not the only periodic table that is in use. Different sciences, whether it be petrology, which is looking at the origin of rocks, or if it's biochemical engineering, you can group elements on the periodic table in many, many different ways. Some of them are grouped by energy levels. Some of them are grouped by what position they occupy in the series, like the lanthanide series or the actinide series. So we can arrange these in a bunch of different ways. They can be arranged on how common they are in the Earth's crust, how common they are in the universe. And so this is just one of them. And you can see just how this one's been sort of put together. So all of these elements in here would share similar properties. And we can see, those are our transition metals. If we look here, there's our alkali metals, our group 1. There's our noble gases here, from helium going all the way down to radon. And so these can be arranged in any way that makes sense to the science that you're looking at. Once again, this is kind of an interesting one, but we can see our gases, our noble gases here, sort of grouped together, and then other groups and families as well. And so our periodic table is not the only way to organize the elements, but it is a very concise and impressive way that Dmitry Mendeleev was able to put together. And he actually got an element named after him, which is a pretty cool thing. Not many scientists get that. And that should wrap us up, because we don't have I'm not going to give you guys homework on it, because obviously we have our CK12 work, and there's some little fun chemistry jokes for you. So the element of surprise, element of confusion, and some fun things you can do with the periodic table, like spell out tacos and bacon. How neat. There used to be I shouldn't say used to be, but there's a pretty popular chemistry lesson that teachers will give. I shouldn't say lesson, but activity, where you spell your name using the periodic table of the elements. Well, that's all well and fine, but my name is Jason, and there ain't a J on the periodic table, so I never liked that assignment. Anyway, I probably bored you to death. I hope you learned a little bit. This will be up very shortly, and I wish you all the best of luck on your CK12 work.